Okay, so the plan for today is to finish up the chain rule and work through implicit differentiation and get a good start on derivatives of logarithms. Before we get started on that, are there any questions on anything from last time, anything from the chain rule worksheet, which is the first thing we're going to review today, anything from the homework, anything like that? Okay, the quote of the day today is uh, that one physical test is worth 1,000 expert opinions. Um, you know, um, much of our sciences, or I guess really all of our sciences, essentially are experimental in nature, right? So we have physics and we have theoretical physics models, and they're really nice mathematical models. But if you come up with a super nice, elegant mathematical model for something in physics or chemistry, I don't care how nice or how elegant it is, if it disagrees with experiment, it's wrong in that context, right? So, I mean, some caveats and so on, is it close enough for what we need for a certain application or whatever? Um, but the point is in something like physics or chemistry, um, the end question is, does it mesh with experiment? Where in math, we develop models that just kind of follow the logic. And we've discussed a little bit in the past about applied versus theoretical math and so on. But I think that's one of the big differences between kind of mathematical thinking and the more empirical thinking is, you know, if somebody says, why is that true? What is your answer to that? If I claim 1 + 1 = 2 and you say, why is that true? Eh, in a math course, I'm probably going to say something like, well, that's one of the assumptions we're making so that we can proceed forward with, you know, addition and multiplication and all of these kind of things that we want to proceed forward with. In something more like physics or chemistry, it's going to be, well, look at this experiment. 1 + 1 = 2 does a good job of modeling. You have one apple, you put another apple next to it, you now have two apples. Um, so just the difference in thinking. And uh, in very many of our subjects that we study, we always want to be thinking back to the physical test being really the something like the arbiter of truth. It doesn't matter how important the person is that's saying that this thing is true, or how nice and beautiful their mathematics or their model is. If it disagrees with experiment, it's wrong. Of course, not just disagreeing one time in one case with one experiment, but so some caveats to that, but I think you get the point. Okay, so let's review the chain rule worksheet. I'm not going to go through every one of these. Like, for instance, this derivative I'll leave. I just gave the answer here, and the same with number 6, but we'll go through the other 5. Okay, I've had a couple of questions about the chain rule. So or sorry, the quotient rule. So let's actually do this problem, which uses the quotient rule. Now, again, recall that the chain rule says the derivative of f of g of x equals f prime of g of x times g prime of x. Or we can think of it as like dy dx equals dy du times du dx. Could phrase it kind of either way, depending on what suits us best for that problem. So my goal is to take, say, a big f of x, a big composite function, break it into the composition of two smaller functions, so to speak, and not just to decompose it, but to decompose it in such a way that each of the two component functions is also easy to differentiate. Quite often, like in this case here, we could probably find 3 or 4 different ways to decompose this that look somewhat reasonable. But we want kind of the like Goldilocks decomposition that puts just enough complexity into both f and into g that we can differentiate them both. If I put too much complexity in the g, I can't differentiate g. If I put too little complexity into g, I probably have a mess left over in f and I can't differentiate that one easily. But here I might say, okay, it looks like I have something to a power is kind of the main thing going on. So if I had, say, f of t equals t to the 5th power, what would that make a g of x? well, g of x would be the quotient x over x plus 1. And this looks pretty good, right? The composition does make my original function x over x plus 1 all to the fifth. I can differentiate f really easily, just 5t to the fourth. And I mean, g is not going to be super pretty, but I could do it. Okay, so what is f prime then? Just 5t to the fourth. And what is g prime? Well, I know with my quotient rule, I have an over the bottom squared. And then I take bottom derivative of top minus top derivative of bottom. And it looks like this numerator, I have an x minus x. It looks like it all simplifies to just 1 divided by x plus 1 all squared. So I think that's what g prime is. And then my whole derivative is what? F prime of g. So 5t to the fourth, but plug in g, times g prime of x times 1 over x plus 1 squared. And that's my answer. I might be able to do something like, oh, I don't know, 5x to the fourth over x plus 1 to the sixth. Maybe that's a little bit simpler, but I I think it will be perfectly fine to leave it this way. And again, we get better at the chain, we're just more proficient at it. We can say, okay, the overall thing being done here is stuff to a power. I differentiate that like a power function. I get 5 times stuff to one smaller power, 5 times stuff to the fourth, times the derivative of the stuff inside. And I probably would still have to come off to the side and differentiate x over x plus 1 by itself, just so that I don't get, it's easy to get things backwards in the numerator, get a sign wrong or something like that. So I still probably would come off to the side and differentiate x over x plus 1 by itself. Any questions on that one? Now, like I said, I'll leave this one. I'll keep it in the exercises, but just gave you the answer here. But what you would do here is this is a product, so make sure you use your product rule. Derivative of the first times the second plus the first times the derivative of the second. And of course, the derivative of the second, the derivative of e to the negative x squared, that's the bit that's going to use the chain rule. So we would have f of t as e to the t, and g of x is negative x squared, and we can proceed from there pretty straightforward, or in a pretty straightforward manner. All right, let's take a look at problem 3. The derivative of sine squared of theta. Now first, let's write this in a little better notation. It always kind of irks me that these trig functions get to have like special notation, Every other function, like with an exponent 2 or with a superscript 2, would be like apply that function twice. But the trig functions get this special notation. But anyway, this is what we have. Now we can do this 2 ways. I suppose we could do this with the product rule, right? So this is the derivative sine theta times sine theta. Or that is 1 times the derivative of the other one plus, well, it's just plus the same thing. So it's just twice sine theta cos theta, or that's just sine of 2 theta by a trig identity. So with our product rule, we get that as the answer. With our chain rule, what do we get? Well, again, I have something squared, so I can say that f of t equals t squared, and that would make g of x, or g of theta. G of theta would be sine theta. F prime of t is 2t. And g prime of theta is cos theta. So then what do I have by my chain rule? F prime of G. So that's 2 sine theta. That's F prime of G, just substituting sine theta in for T times G prime of theta cos theta. Get exactly the same thing. Any questions on that one? Okay, let's also look at deriving the quotient rule using the chain rule. And the key is to think of the quotient as f of x times g of x to the minus 1 power. And then what do I want to do? Well, my product rule says take the same product twice, add it together, differentiate one factor in the one product or in the one term and the other factor in the other term. So I have an f prime of x times g of x to the minus 1, or that's just an over g of x, plus f of x d by dx of g of x to the minus 1. Get my parentheses all straight here. And of course, this is the bit where we're going to use the chain rule because we have derivative of something to a power. And what does this tell me? This says I bring the power down. I subtract 1 off the power. So minus 1 minus another 1 makes a minus 2. Be careful when you have a negative power that you kind of go the right direction. Subtract 1 off the power means take the power minus 1. It's easy to make the mistake and just kind of bring the power closer to 0, going the wrong direction when you have a negative power. So negative 1 g to the negative 2 times g prime from the chain rule. So this step was using the chain rule. And what does this give me? Well, this gives me, I see I need a over g squared here. I have f prime g over g squared plus f g prime over g squared. And I have this minus 1, so let me just kind of cheat and slide that in there. Or I have bottom derivative of top minus top derivative of bottom over bottom squared. That looks good. Now, typically, if I was dealing with a specific f and g and I didn't want to use quotient rule, I would stop here and actually just take this derivative. I wouldn't put everything together, like these extra couple of steps show, but I would stop here and differentiate g of x to the minus 1 power. But if you do that, don't forget that you still have a product rule that needs to be taken care of. So there's still all these other pieces coming into play. So you really do have to, be careful, take care, set it up this way, make sure you do all your product rule steps, and then you can do that derivative of g to the minus 1 power. Okay, number 5, this should be a pretty straightforward one at this point. So derivative of sine of 2 theta. Again, it's really tempting in problems like this to say, oh, that's like almost sine of theta, and just say, oh, its derivative is just cosine of 2 theta and be done with it. But we have to be just very careful, right? I mean, we know the derivative of sine of theta is cos theta, but that we only know that exactly. Sine of 2 theta is pretty close to sine theta, but it's not exactly the same. We could maybe use a trig identity here in the product rule. That might be another method to investigate if you're looking for some practice. Oops, went a little too far. But here I think I want f of t to be sine t and g of theta to simply be 2 theta. Not a massively complicated g, but still necessary for kind of what I call like the bookkeeping or the accounting, just keeping all of these details straight so that when you're tracking through a problem, you have some assurance that all of these little details are being handled. We're not going to end up off by a negative or off by a constant factor or something like that. F prime of t is cos t and g prime of theta is not just 1, but it's 2. It is just a constant factor, but it's important to have it in there. And what do we end up with from our chain rule? F prime of g cos of 2 theta. So like almost what we would have got if we just naively applied the derivative of sine as cosine without thinking about it. But we have an extra factor of 2 from the chain rule. So really easy if we're being a little careless to get off by just a small constant factor or a multiple of -1 or something like that. Number 6, we come up on this one and we actually notice when we get to the end that we get the derivative as sine of 2 theta. And that might ruffle our feathers a little bit because the derivative of sine squared theta was sine of 2 theta. But supposedly the derivative of negative cosine squared theta is also sine of 2 theta. I have two different functions. How can they have the same derivative? We kind of discussed at the end of chapter 2 that kind of roughly speaking, as I mentioned down here, derivatives ought to be unique up to a constant term. So if I have one function and I find its derivative, I shouldn't have a completely different function have that same derivative. I wouldn't expect that. So what's going on here? Did anybody come up with an answer to number 7? The rest of these are pretty procedural. This is a little bit of a deeper answer. Any thoughts on this? Well, it turns out that cos squared theta and sine squared theta are like almost the same function. Of course, through our Pythagorean identity, they're definitely related. And we see that sine squared theta is indeed just negative cos squared theta. That's just the same function, but up to a constant term. We have a little, +1. But this is actually what we would expect. If we think a little more deeply about it, we do recognize that, oh, okay, these sine squared theta and negative cos squared theta are really the same function up to that constant term, just adding 1. So it actually does resolve in a way that that's satisfying, right? So a little bit paradoxical at first, but it worked out okay in the end. As kind of a side note, that's one of the I guess maybe sometimes positive and sometimes negative things about trig functions is there are so many identities and so many ways to rearrange things and rewrite things that on one hand, sometimes you work through a problem in the textbook that has a trig function in it and you get an answer, and then you look in the back of the book and there's what seems to be a completely wrong answer, or it seems to suggest that your answer is wrong, but maybe they aren't, maybe they're actually the same and just, I mean, if you get like 2 sine theta and the book got 1 sine theta, that's probably wrong. But if you have a big trig expression here and a big trig expression there and they don't look quite right, maybe head on over to like Wolfram Alpha or your graphing calculator and maybe evaluate the expressions, both of them at a couple different points, and see if you get the same answers or if you can graph them and see if they're like the same graph. Sometimes you have the same thing just written in 2 different ways. And that's kind of the case here. Okay, any questions on the correlation or correlation regression is on my mind from stats, I guess, on the chain rule worksheet. Okay, so let's finish a couple more examples in the chain rule section, then move on. So one idea that's super important across a lot of the applied sciences, so engineering and physics and chemistry, even biology and some of those what we might call like the softer sciences, the less less mathy kind of sciences to in some sense. Um, a very important idea across all of those is the idea of differential equations. What is a differential equation? Well, let's actually look at a simpler example first. We might have a differential equation like this. Y double prime plus 4y equals 0. Doesn't get a whole lot simpler than that. So really what a differential equation is it's an equation that relates a function to one or more of its derivatives. In this case, this equation is relating the function y equals f of x to its second derivative through this equation. My goal in finding a solution to such an equation is to find a function. I'm looking to solve for a function, y equals f of x, that when I plug it in here, satisfies this. So for instance, just a little aside, I might think of the differential equation y prime equals y. So this is a little aside. And I'm looking to find a function that, when I substitute in here, satisfies this relationship. And of course, y equals e to the x works, because the derivative y prime is e to the x. Is that equal to e to the x? Yes. So y equals e to the x is a solution to y prime equals y. Now, there are some extra complications, things like there might be more than one solution, there might be infinitely many solutions, and so on. But the goal of Calc 1, when we see differential equations, is really not to do this step. It's not to say, here's a differential equation, find the function. We actually have a whole course called differential equations where that is the goal. So we build up to being able to solve these kind of from first principles. But in Calc 1, what our goal is given a candidate function, I think a function that looks something like y equals sine of alpha x squared, and given a differential equation, can I maybe either prove that this function does solve this differential equation, or maybe I have a degree of freedom, something very often that comes up in engineering. You insert a degree of freedom, something that you can tune to your particular problem, and then you figure out what that parameter ought to be. So y equals sine of alpha x squared. I want to show that it is a solution to this differential equation, or maybe in another example down here, alpha is serving a different role. I have y equals alpha t cos 2t, and I want to find the value of alpha that makes this solve this equation. Or down here, I have a function y equals e to the rx. I want to find the value or values of r that make this function satisfy this differential equation. So those are the kind of things we'll be looking at doing in Calc 1, either just demonstrating that a certain function actually is a solution to the differential equation, or maybe going a little bit further and picking the value of the parameter that makes it a solution. But in Calc 1, we would never say, here's a differential equation, find the function that solves it. That's a question for a full differential equations course. Okay, so let's go through this then. What is my goal? My goal is to find the derivatives of y, its first and second derivatives, plug them in, and hopefully show that everything goes away on the left-hand side, right? Because we want equals 0. Okay, so let me come over here. I have y equals sine of alpha x squared. I need y prime and y double prime. So what is y prime? I have sine of stuff. That differentiates to cos of stuff. Then the chain rule says now multiply by the derivative of the stuff inside. The derivative of alpha x squared is 2 alpha x. So that is y prime. What is y double prime, the second derivative? Got to be a little careful here. I need to use the product rule. So I'll differentiate the first times the second plus, so that 2 alpha x just differentiated to 2 alpha. The cosine of alpha x squared just copies down. Plus the first, in this case 2 alpha x, we keep the x, times the derivative of the second. The derivative of cosine of stuff is negative sine of stuff. Let me change that sign. So negative sine of stuff. And then times the derivative of the stuff, times the derivative of stuff inside. Times 2 alpha x. Or what do I end up with? Two alpha cos alpha x squared minus 4 alpha squared x squared sine of alpha x squared. Okay, so let's come over here and plug these in and see if everything cancels. So y double prime, I'm going to write these kind of one on top of the other. Y double prime is 2 alpha cos of alpha x squared minus 4 alpha squared x squared sine alpha x squared. So that's my y double prime term. Minus 1 over xy prime. Well, that's minus 1 over x gets rid of this factor of x. 2 alpha cos of alpha x squared. So this bit came down here. And we see that these go away. That cancels out my first term of the y double prime bit. And then plus 4 alpha squared x squared times y sine alpha x squared. And I see again, I have some nice cancellation, minus and plus the same thing. This whole left-hand side nets out to be 0, which is exactly what we're looking for. So this function is indeed a solution to that differential equation. Any questions on that? So let's look at an example down here dealing with resonance. So here we have something that we might think of as like a mass spring system, like a harmonic oscillator. Y double prime plus 4y. We have kind of an inertial term, like an F equals ma term. That's the y double prime here. And then we have like a Hooke's law kind of term, a restorative force here. We don't have a first derivative term. We know that first derivative is related to speed, and speed relates to the way things move by basically the faster that you're going, the more air resistance or drag or friction that you experience. So we're thinking of like a frictionless mass spring system here. And we also have an external force that's like pushing it over time. So this might be a little bit kind of like, we also see that it's an oscillatory force. We might think of this something like a kid swinging on a swing. A pendulum, a swing is kind of more or less like a mass spring system some of the time. So we might think of a kid like swinging on a playground swing set and like the parent pushing them, right? The parent's pushing them at a certain frequency, you know, once every 3 seconds or something. They're putting energy into the system a little bit more. That's a little bit like what this is doing. Of course, this is more of like a continuous up and down transfer of energy, but we can imagine this as being like a parent pushing their kid on the swing kind of a deal. We have a restorative force. Gravity wants to pull the kid so that they're straight up and down. We have an inertial term. that if the kid's moving backwards, they're going to keep going backwards for a bit and vice versa. And we have an external forcing term like the parent pushing the kid on the swing. So it turns out that to solve this differential equation is actually not easy at all. We would be probably about halfway through the differential equations course by the time that we would be able to solve this from first principles. But here we're getting quite a bit of help along the way. So part A is, well, we want to find what we call the homogeneous part of the solution. This is basically if we just took away this forcing term, if the kid just started hanging at a certain place on the swing and then we let them go and watched what happened, that's the homogeneous part of the solution, if we ignore the external forcing term. So we're looking to find omega so that this linear combination of sines and cosines solves y double prime plus 4y equals 0. Why would we think that such functions might solve this? Well, I kind of was able to guess up here that y equals e to the x because I'm looking for a function whose first derivative looks like itself. Well, note down here, y double prime plus 4y equals 0. We could write that as y double prime equals negative 4y. I'm looking for a function, roughly speaking, whose second derivative looks like negative itself. Well, that kind of seems like the trig functions. So that's why, as a gut feeling, I might think that trig functions might work here. And also, if I know what's being modeled here, even without the sine of 2t term, if I got rid of that and just made this 0, I can just think of, picking a kid, pulling a kid back on the swing, holding them still, and then just letting it go and seeing what happens. No external forcing term. But they would still kind of go back and forth in a cyclic manner. So, okay, so I need to find the second derivative of this proposed homogeneous solution. So let's find its first derivative. A times cosine of stuff becomes A times negative sine of stuff. But don't forget the chain rule. We have an omega t on the inside. We multiply by omega. So roughly speaking, we have cosine of stuff. When its derivative, it differentiates the negative sine of stuff times the derivative of the stuff inside. And then plus b, derivative of sine of stuff is cos of stuff. Again, times the derivative of the stuff inside. Or writing this a little nicer, this would be like negative a omega sine omega t plus b omega cos omega t. That's the first derivative. I need the second derivative. Note that I didn't pop out anything to do with t, the independent variable. These omegas came out, but those omegas are just constants. So the second derivative is actually going to look pretty similar. Note that up here on the last one, when I took the first derivative, I had an independent variable come out, which made the next derivative more difficult. I had to do a product rule first because I had an independent variable floating around. I don't have that in this case. So again, I differentiate. So this negative a omega is just a constant. Differentiate sine omega t to cos omega t. I pop out another omega. So this is negative a omega squared cos omega t. And then for my second term, this b omega, again, is just a constant. It comes through the derivative. The derivative of cos omega t, the derivative of cosine of stuff, is negative sine stuff. But my chain rule pops out another omega. So I get b omega squared. Or what do I see? I see that I want y double prime plus 4y equals 0. Or I want negative a omega squared cos omega t minus b omega squared sine omega t. That's y double prime. And then plus 4y. So that's plus I'll write it as A times 4 cos omega t plus B times 4, let's say 4 sine omega t. And this has to net out to 0. And we see, of course, that omega squared has to be 4. And let's pick omega to be 2 because we're plugging it into a trig function. We have symmetry anyway, so it's not that big of a deal. But if we chose it to be -2, but let's choose it to be the nicer of those. So we have omega equals 2, or in other words, for any choice of A and B, any real numbers you want, number times cosine of 2t plus number times sine of 2t solves this homogeneous equation. If you just pull the kid back and hold them still, let them go, and don't push them, they're just going to swing back and forth, just oscillating back and forth basically forever in the absence of air resistance and friction and, rolling friction from the chain attaching to the top and all of that. Of course, that's a consideration in real life. The kid wouldn't keep going forever, but we're not including that in our model. So maybe for the first swing or two, this might be an accurate model. For the 1000th swing, this is going to not be very accurate at that point. Now we might be interested in answering the question, okay, now I want to consider the model, the part of the model with the external force, with the parent pushing the kid now. We're forcing the system at essentially at an omega of 2 as well. So I'm actually forcing the system at what we would call its natural frequency or its resonant frequency. When I'm looking for a particular solution, that particular solution, YP, is the solution that models this external forcing term. It's the part of the solution that takes care of that. And again, how did we come up with this? Why did we know this was the right function to choose? That's a question for a differential equations course. But for this particular exercise, we're given the form of the function. Our particular solution we're looking for is alpha times t times cos of 2t. And we want to find alpha, find the value of this parameter, so that this solves the full differential equation, including the external forcing term sine of 2t. And I'm leaving this as an exercise so you can work through. It's kind of similar to a combination between part A and this last problem here. And the answer is alpha is -1/4. And our general solution to this differential equation is the sum of the two. So what do we say? Omega was 2. That was our homogeneous solution, kind of modeling the system itself without the external forcing term. And then -1/4 sine of 2t. Oh, -1/4. I was looking at the wrong thing. -1/4 t cosine of 2t. That's the entire point of this problem. So these just kind of sit there and do their thing over time, right? Nothing super interesting happens with these. They just combine to make one sinusoidal, and they just do this. What does this do, though? Cosine of 2t doesn't do anything super interesting. It just goes back and forth. But it has an amplitude t. Over time, this dominates by far, right? When we're forcing a system at its resonant frequency, we essentially keep adding energy into the system, right? The same way that if you like push your kid and they go forward a little bit and come backwards, if you wait until they come all the way backwards and you push them a little bit again, they go forwards a little further, come backwards a little further, you push them a little bit again, they go forwards even further. you kind of build up this energy that's in the system. Now, if we force that not its natural frequency, if you push the kid and kind of they go up, and when they're coming back, if you push them again if you push them this way while they're coming back this way, aside from that being super annoying and uncomfortable, you're kind of like sapping energy out of the system, right? Sometimes you're going to make them swing a little higher, sometimes you're going to stop them altogether, and sometimes it's going to be something in between. But when you force at that resonant frequency, a lot of interesting things happen. Again, this is, of course, in the absence of any friction, air resistance, drag, noise production, anything like that. So, um, in reality, this amplitude isn't going to go to infinity, uh, but in the model it does. And certainly in reality, in many cases, that damping is small enough that this will become the dominant bit, and forcing at the resonant frequency actually um, is very applicable to a lot of different applications, things like tuning a radio and all these kind of things. All right, any questions or thoughts on this problem? So just to be very, very clear, it is not a Calc 1 question to say, here's a differential equation, find the solution, right? Um, this is the Calc 1 problem. Here's a proposed form of a solution to a certain differential equation, find the parameter that makes it a solution, or check that this proposed solution actually is a solution of the differential equation. But I figured, that a lot of you are going into applied fields, you might appreciate something like this that's a little more applied. And if you look up a Wikipedia resource or a physics textbook or something on resonance and its applications, very interesting stuff. There's all kinds of applications of resonance and very real, very practical applications. I know that sometimes in math we're like, let's do an applied problem, and it's like, still 9 out of 10 parts abstract. But I think resonance is pretty solidly in the applied side of things. Okay, so let's look at one more example. Here we have, again, what we would call a second order differential equation. We see a second derivative. And we're looking to solve this differential equation, y double prime minus 4y prime plus y equals 0. We see we have a linear combination of a function and its derivatives. We want it to be equal to 0. We're going to guess a solution of the form y equals e to the rx. Why do we do that? Well, because we know that the derivatives of e to the x type functions look like themselves. I need a linear combination of a function, its first and a second derivatives, to be 0. I need these to combine together nicely so that they can all cancel out and be a 0. I mean, some kind of e to the x thing is the natural guess for something like this. Why do I have the value r in there, that parameter r? Well, I mean, if y equals e to the x were to solve, y double prime minus 2y prime plus y equals 0, it's probably not going to solve a similar question with a minus 4 there or a plus 6 there. I need a degree of freedom, at least 1 degree of freedom, so that I can kind of tune my solution to the particular differential equation I'm trying to solve. I can adjust that parameter so that I can solve lots of different differential equations. Okay, this should be an easier problem than the last one. We need the first and second derivatives. Well, I have e to the stuff. Its derivative is e to the stuff times the derivative of the stuff in the exponent. Well, that just pops out in r. As an aside, I don't think I mentioned this, but I've kind of transitioned to going quickly through the chain rule. Instead of writing out all over f and g and all of that, I'm going much more quickly. If you're still not comfortable with this pace, if you're saying, wait, where did that come from? When you go back through and look over your notes, come over here and write out your, f and g and so on. Do that until you're comfortable with it. That's not like taking a loss or anything like that. If you're not comfortable with it at this point, that's perfectly okay. It's much better to do that 10 or something extra times and really get it down than to say, okay, I'm just going to kind of, fake it till you make it or whatever they call it these days, So if you're not getting this, if you're not, if it's not clicking for you where all this comes from, go through and write your F and G, write it all down carefully. But I would recommend, drilling it hard in the next week or so and trying to get it to this level of fluidity, I guess. Okay, and then the second derivative, well, the R is just a constant. So again, I need to differentiate e to the Rx. That's e to the stuff, differentiates to e to the stuff, times the derivative of the stuff. Well, that's just another factor of R that comes down. That's just R squared, e to the Rx for the second derivative. My differential equation is y double prime, R squared to the Rx, minus 4y prime, R e to the Rx, plus y, plus y is this one, e to the Rx equals 0. I know that e to the Rx, well, it's in every term. I can factor it out, and I know that e to the Rx is strictly bigger than 0. I can divide through by it, no problems with that. And I'm left with r squared minus 4r plus 1 equals 0. But hey, this is just a quadratic equation in R, my parameter. I've changed a differential equation into an algebraic equation by a creative guess for my form of my function. I was able to do that. And this algebraic equation, of course, is easy to solve. We just take R as negative b plus or minus square root of b squared minus 4 times 1 is just minus 4 over 2. Or that is what? 2 plus or minus root 12 over 2. That's square root of 4 times 3 over 2. The 4 comes out as a 2. That's just square root of 3. So r equals 2 plus square root of 3. That's one number for this parameter that would satisfy this differential equation. R equals 2 minus square root of 3 is the other. And no other R is going to satisfy this. Any questions on anything in chain rule? Like I've kind of mentioned before, this is kind of like the over the hump material. Like if you get this really well, a lot of the stuff in the future is going to make sense, actually starting with implicit differentiation. It's going to make sense much more easily. Or even if chain rule isn't directly applicable to this new thing we're learning, I mean, we're dealing with compositions of functions all the time. So they're just naturally going to kind of come up in a lot of our problems, probably half or so of the problems from this point forward. So if you understand it really well, it's going to make everything else just go that much more smoothly. If you're struggling with it, if you don't remedy that, it's going to, come back to haunt you in every section and every homework you do on every exam. So it's one of those things, if you're going to take the extra time to put into one section, make it the chain rule. Make sure that you're really squared away with this material. Okay, so jumping down to our next topic, implicit differentiation. So implicit differentiation is kind of roughly speaking, differentiation of implicit functions. So let's look at a motivating example. Let's try to find the rate of change of y with respect to x at the point xy equals 1, 0 for this relation. E to the xy minus x squared plus y squared equals 0. No way we're going to solve this for y in terms of x and make it a nice looking function. Even something like, x squared plus y squared equals 1 circle. I mean, okay, that's a relation, but we can kind of take the top half and the bottom half and make each of those look like nice functions. We can maybe, do some acrobatics and get around the need to treat it like an implicit function. But something like this implicit relation, really not going to be able to do anything to make a nice like y equals f of x kind of a situation pop out of here. All right, if we look at a plot of this function, it looks something like this on this window. And I see the point of interest is, say, x equals 1. Now, I might be tempted to just say, okay, I'm looking for the derivative at x equals 1. That would be like here. But if I say something like that, I have a little bit of an issue. Let me actually just move it over a little bit so I can illustrate better. This wouldn't be where x equals 1 is, but it's going to be a little hard to illustrate right there. I have a little bit of an issue if I just said, find y prime at x equals 1. Well, which one do I mean? Right? Do I mean find that slope or find that slope? It's unclear, right? Because this isn't a function per se, it's a relation. And one value of the independent variable can have multiple values of the dependent variable associated with it, or vice versa. So the first thing that I realized just looking at the picture is that, well, I expect that a derivative of an implicit function is going to actually depend on both variables, both x and y. So when I write y prime equals something at the end, I expect that right-hand side is probably going to have x's in it and y's in it. Right? That's very strange. We haven't seen anything like that before. We just had a new function of x that came from an old function of x. Here, we're going to have a derivative that's dependent on x and y, but it makes sense when we think about the geometry that to clarify where I'm taking the derivative, I need to tell you actually which specific point I'm taking the derivative at. Because otherwise, if I just told you the x value, you might grab this one up here or something. So and actually, I think I chose the wrong one there. 1, 0 is that one, not the other one. So we should be looking for a formula for the slope of this tangent line. Okay, now how can I do this? Well, let me bring my relation down. Now let's come over here to an aside, and let's say I had, I don't know, y equals x squared. And I could just say, well, what's the derivative? What's this notation? This notation just represents something that means 2x. Okay, I mean, that's a perfectly valid thing to do. But I could think about it a little more granularly than that. I could actually say, what am I doing? I could think of myself as applying an operation to both sides, the same way I might in an algebra problem square root both sides, or square root or square both sides of an equation or something. I can apply an operation to both sides. I could square both sides, I could square root both sides. I could apply differentiation to both sides. Say differentiation with respect to x. So I could apply the same operation to both sides, in this case, differentiation with respect to x. Note that just saying differentiation isn't actually enough here. I kind of have two variables and it's not really clear what role which variable is playing. So I have to be very clear that I'm differentiating with respect to x, right? I asked for the change of y with respect to x. We have to be very clear which one is, from the standpoint of the derivative, kind of being treated as the independent versus the dependent variable, because it's not clear from the relation. Well, if I apply this differential operator to both sides, d by dx of y, well, that's just another way of saying dy dx. And then I can apply the differential operator to x squared, and that gives me 2x. That gives me the same thing. I mean, it's not groundbreaking, but the thought process is apply an operation to both sides of the equation. That's the differential operator with respect to x. Can I do that over here? I mean, I suppose I can. Okay. So I did this. What does this tell me? Well, the right-hand side is easy enough to do. The derivative of any constant function is 0. So I can knock that one off. I guess on the left-hand side, I can use a property of derivatives. I mean, there are some x's and y's on the inside, but still the derivative of the sum is the sum of the derivatives, and same with the difference and so on. So I split the sum or difference apart into the sum or difference of derivatives. And now I actually see another derivative that I can do pretty easily. Well, this one, it's just a regular old derivative. It looks just like that one. This is just going to be 2x. Now, if I want to do d by dx of y, how can I think of that? I suppose on one hand, I can just think of it as the notation dy dx, or I can remember that d by dx of something, I can change the variable I'm differentiating with respect to d by dy of stuff times dy dx. This is, a really laborious way to talk about this, but we'll see that this idea will come in handy in a minute here. So d by dx applied to y by the chain rule, I told you the chain rule will come up again right away, as d by dy applied to y times dy dx. Now it's very clear this is just y prime. But now my variable of differentiation for this first factor is y, and my variable of the thing I'm differentiating on the inside is also y. So this is just 1. It's just y prime. But now I've got the most challenging of them all that we've hopefully built up to slowly enough that we can handle it now. And that is d by dx of e to the power x times y. Well, here, what do I have? I really have the derivative with respect to x of e to a function of x. This is just like some u, let's call it, equals xy. So this would be like d by du, e to the u, du dx. Does everybody agree with that? If I just rename x times y to the variable u equals x times y, this is just d by dx of e to the u, and then by the chain rule, just like I did up here, this is going to be d by du, e to the u, times du dx. Well, d by du, e to the u is just e to the u, du dx, or that's just e to the xy, du dx. I'm making progress, but now I've got to find out what this is. So what is du dx? Well, that's really d by dx of x times y, right? That's just what u is. U is just xy. But I have the product of, that's certainly a function of x. And y is also essentially a function of x, right? Y is dependent on x. If I choose x, that at least restricts the values of y that are permissible. So y acts like a function of x. I need to apply the product rule here. So that's 1 times y plus x times the derivative of y with respect to x, y prime. So y plus xy prime. Lots of details, but again, if we go through just carefully and consistently, I don't think any single step is a huge logical leap, but it's just, putting all of the steps together. Uh, there are certainly a lot of steps here. But what do we end up with? We end up with e to the xy times y plus xy prime. So we have kind of another relation that now involves y prime. And I could do a couple things here. I could just plug in x equals 1, y equals 0 and see what I get. I could absolutely do that. Let me do that here. So when x equals 1, y equals 0, I have what? E to the power 1 times 0, e to the 0 is 1, times y, 0, plus xy prime, y prime plus 1y prime, minus 2x, it's just minus 2, plus y prime equals 0. Or what do I have? I have 2y prime equals 2, or y prime equals 1. Can I believe that? Yeah, sure. Yeah. Slope equals 1. That seems plausible for my picture. I believe that. But what if I wanted to get a formula for y prime in terms of x and y? Again, remember, I need information from both x and y, or I don't know where I'm at on the picture. Well, nicely enough, when I go through this process, this is a big mess, but notice that it's just a linear equation in y prime. I don't see any e to the y primes or any y prime squareds or anything like that. It's linear in y prime, which means I can solve it like any other linear equation. I multiply everything out. I collect my y prime terms together, factor out, collect my non-y prime terms together, isolate the y prime term, and then divide by coefficient. So this gives me y e to the xy plus x e to the xy y prime minus 2x plus y prime equals 0. This and this do not have a y prime in it. I can just go ahead and push those to the other side now, I suppose. So I have x e to the xy plus 1 y prime equals 2x minus y e to the xy. And now to solve for y prime, I just divide by this stuff. I mean, this isn't the prettiest simplification in the world, but I now have y prime as a function of x and y. If I plug in a particular value of x and a particular value of y, I get y prime out. Now, very important, this y prime, it's not valid. This isn't a reasonable, whatever, derivative or something. It's not valid for all x and y in, say, R2. It's not valid for all ordered pairs x and y. Why is that? Well, because this only makes sense when we're talking about an xy coordinate that is on the curve, right? I mean, that's what we started with, was we started with this restriction. So, I mean, I could evaluate this function on the right-hand side for essentially any xy combination I want, I guess, as long as the bottom is not 0. But, it's not really a sensible derivative in any sense, except for those xy coordinates that lie on this curve. The coordinate 1 comma 0 lies in the curve. We see very clearly that if I plug in x equals 1, y equals 0, I end up with e to the 0 minus 1, which is indeed 0. So that 0.1 comma 0 does lie on the curve. So this y prime represents a derivative. It represents a slope of a tangent line to this curve, provided that I plug in x, y ordered pairs that are actually on the curve. If I plug in some random number out here, I might get some number that I'm saying is a derivative, I'm saying is a slope, but that doesn't really make any sense. So not for all xy, but for xy on the curve. So all in all, if we're really good at the chain rule, this actually isn't a big deal, right? If I want to do implicit differentiation, I just change my thinking a little bit and say, okay, I just apply the differential operator to both sides of the equation. I take my time. I just make sure I'm super careful with applying derivative rules properly. Whenever I run into a d by dx of a function of x, I just differentiate it like I've been doing, no big deal there. If I run into a d by dx of a function of y, I need to make use of my chain rule, right? So, well, I erased it now, but I kind of made this xy into u and made a d by du of e to the u times du dx using my chain rule once there. And then also kind of, I suppose, a slightly tortured view of this like d by dx of y, thinking of that as like d by dy of y times dy dx. But again, that concept is what we kind of apply a little more generally. And the other nice thing is that when we do this differentiation, the y prime that pops out from the chain rule always pops out as just the times y prime. So we always just end up with a linear equation in y prime. It might be a bunch of messy things to write down, but the strategy is not complicated. We solve it like any other linear equation in a variable. We isolate the variable term, we isolate the variable, and we're done. Any questions so far? Okay, so let's move on then to derivatives of inverse trig functions. So here we're going to introduce kind of an idea that we can use, we can leverage alongside implicit differentiation to take derivatives of inverse functions. So here let's consider y equals arctan x, or the inverse tangent of x. Note that this is not 1 over tangent of x. This is the inverse tangent of x. And we want to compute y prime. Again, you know, trig notation coming to bite us a little bit. This is not like, you know, negative tan to the negative 2 of x times something. It's not like that. This is inverse tangent of x. So where can I even get started with this? Well, I can recognize that I don't know how to compute the derivative of inverse tangent, but I do know how to compute the derivative of tangent of something. And to be clear, what's y prime? By that, I mean dy dx. I can move the tangent to the other side. The relation y equals arctan x can be rewritten as tan y equals x. Now, this is a lot nicer because when I try to differentiate, I have to differentiate a tangent of something, and I know how to do that already. Derivative of tangent is secant squared. But it's a little bit less nice because I want to take my derivative with respect to x, but the complicated stuff is now attached to y, not to x. Up here, I had complicated stuff attached to x, so it was in line with the variable I want to differentiate with respect to, but the complicated stuff was a little too complicated for me to deal with. So I've got my stuff less complicated, but with the increase in complications being, I now have this mismatch of derivatives. But let's see what we can do with this. We can apply the differential operator to both sides. Now that right-hand side, well, that's super easy. That's just one, right? D by dx of x, that's just the regular old standard derivative from section 3.1. D by dx of tan y, this is where our chain rule comes in nicely. This is d by dy tan y. That's what I would really like to do, times dy dx. That's what our chain rule lets us do, effectively switch the variable of differentiation. But d by dy of tan y is just secant squared y, and dy dx is just y prime. And at this point, I can solve and get y prime equals 1 over secant squared y. And I have my answer, right? Y prime equals 1 over secant squared y. I have y prime as a function of x and y, which is what I kind of expect from up here, right? Y prime is a function of x and y. Now it turns out that I can do a little bit better here. And why is that? Well, y equals arctan x, it's an actual function. Kind of what I was using here is I kind of chose to write it as an implicit function in a way, an implicit relation, but it's an actual function. In other words, if I know x, I know exactly where I am on the graph. There should be no ambiguity. So unlike this one up here that was truly just a relation and really not a function, I definitely needed to know my y coordinate as well as x to know where I'm at on the curve. Well, this one down here, it seems like I should be able to get away with knowing just x, and I should be able to write my derivative in terms of, well, in terms of the independent variable that I started with. Well, what do I have? I guess I can try to rewrite secant squared y in terms of something else. I know that sine squared theta plus cos squared theta equals 1. If I want to make a secant squared of something out of there, what do I need? I guess I need to divide by cos squared. Tan squared theta plus 1 equals secant squared theta. So it looks like secant squared y is 1 plus tan squared y. But wait, what's tan squared y is tan of y squared. Again, sorry for the crazy trig notation. I didn't make it up. But wait, tan y is x, so tan squared y is just x squared. So in this case, because we started out with just a regular old normal function, we used this kind of trick to put the complication on the other side, on the y instead of the x, and did implicit differentiation. But we weren't forced to use implicit differentiation. This wasn't really an implicit function we started with. We used that as a technique during our solution method. We really ought to return the result in the original independent variable that was asked for. And here we're able to do that. So I probably wouldn't want to leave the result here. I would definitely want to go that extra step and return the answer in the independent variable that was originally stated. I cannot do that up here. It's just not possible. If I tried to return the answer just in terms of x, that just doesn't work. There are going to be two different slopes associated with that x. I need to be able to distinguish between them. The only other way I can distinguish between them is by having some y's in there as well. But I can definitely do that down here. Any questions so far? All right, let's look at the derivative of arc cos. So if y equals the inverse cosine of x, what is y prime? We'll leave as an exercise computing the inverse sine derivative. But we'll use the same strategy, right? Cos of y equals x. And then we take d by dx of both sides. On the right side, we have just a 1. And on the left side, well, this is really d by dy cos y. So this is negative sine y times dy dx times y prime. And again, I get y equals negative 1, y prime equals negative 1 over sine y. And again, if we were starting with an implicit function, having some y's on the right-hand side, no big deal. We were starting with an actual relation where I need that information. But here again, I'm starting with an actual function of x. I should be able to massage this and get y prime as a function of x. Let me try to do that. And there's kind of, I guess, two ways that I can go about this. The first, I can use a more geometric approach. So let's take a look at that. So I'm saying that cosine of y equals x. So I have some angle that I'll call y, and the cosine, the adjacent over hypotenuse, is x. So let's call this x and that 1. So now cosine of y equals x over 1 or x. Pythagorean theorem forces the third side to be what? I want x squared plus this squared equals 1. So that's square root of 1 minus x squared. So cosine of y equals x, by the way, I set it up. I found the third side with the Pythagorean theorem. And then what's sine y? Opposite over hypotenuse, root 1 minus x squared. So I can rewrite sine y as negative 1 over square root of 1 minus x squared. That's probably the best way to go about it. The other way I could do it, if I wanted to stay more in the algebraic world, I could look at y prime squared as 1 over sine squared y, which is 1 over 1 minus cos squared y, 1 over 1 minus x squared. But now I have an issue where y prime is plus or minus 1 over root 1 minus x squared. Clearly, it's not both, right? My arc cos cosine looks like this. If we flip it over the line y equals x, arc cos looks like this. Clearly, if I pick an x, it's like it's going to have some slope. It's not going to be like plus or minus that slope. I can pretty clearly see that the slope has got to be negative just by looking at the pictures. That's not a very good proof. We probably, would have to do a little more work to argue this, but so we can see that it's going to be the negative slope. But you can see how you could kind of manufacture a situation that looks a little more similar to how we went about the tan squared or the secant squared turning into tan squared. We have a similar argument here, but we have this kind of messy have to square it and square root it, and that introduces a plus or minus, and we got to get the sign right. So maybe in this case, the more geometric approach is maybe a little more straightforward. Again, as an exercise, do the same with arc sine. You should come up with a pretty similar looking result. Just make sure to get your sign, SIGN, right? Plus or minus. But yeah, should be a pretty similar result for arc sine. I think we're going to skip over this example and move on just for the sake of time. We've got about 20 minutes left, and I do want to get at least through kind of an introduction to logarithms and the crash course on logs. before we break for today. Any questions so far with chain rule or implicit differentiation? So main idea with implicit differentiation is you're kind of just applying chain rule under this new idea of I can just apply differential operator to both sides, and then being able to use the chain rule pretty freely and flexibly is immensely helpful with that. Okay, so we previously did a primer on exponential functions, and we did kind of a crash course. This is going to be similar. Primer on logarithms is going to be kind of a crash course. If you want a little more in depth or more practice or anything, going to like a pre-calculus book or video series or Khan Academy or something would be a great place to look at. Or even our book has a little more information on logs, I think, in the front of the book. But this is meant to be kind of a crash course, so it's going to be a bit fast-paced. But here we go. So if we think back to our exponential functions, we have functions like y equals a to the power x. Here a is positive and not equal to 1. We call a the base, and of course x the exponent. We let x be any real number. If I take a number like 2, or even if I take a number like 2 or even 1/2 to any real number power, I'm fine with that. The outputs are always positive, so open 0 to infinity. And we say that the domain is all real numbers, and the range is the positive real numbers for my exponentials. Now, what is a logarithm? A logarithm is the inverse function of the exponential function, or of an exponential function. So if it's true that y equals a to the x, we could equivalently say that x equals what we call log base a of y. So we would say if y equals a to the x, then x equals log. I usually write my logs, my first L is a cursive L. I just find that if I do something like this, sometimes this looks like a 1, sometimes it looks like an absolute value sign. That's just a little quirk of mine, I suppose. But so log base A, so we would say log base A. That's our base from the associated exponential function. That's why it's called log base A of y. So the function is log base A, and its argument, the thing being plugged into the function, is y. The A is written as a little or a little subscript here next to log to indicate what the associated base is. So y equals 2 to the x, that exponential function has an associated logarithm, y equals log base 2 of x. Those are the two inverse functions. When I move from a function to its inverse function, I essentially flip the graph over the line y equals x, and I exchange the roles of x and y. I still have my same restriction on the base a, log base a of y. The base a still has to be positive and not equal to 1. I still have that, be careful here, x equals log base a of y. I have that x is all real numbers and y is positives. But I see now that what I can plug into the logarithm function is positives. And when I get out of the logarithm function, the range is all reals. My domain and range swapped when I went from one to the other. So the domain of an exponential function is all real numbers. Its range is positives. The domain of a logarithmic function is positives, and the range all real numbers. Let's look at a couple of graphs. So kind of our standard, our standard y equals, say, 2 to the x or something like that. 2 to the power x looks like this. If I were to flip this over the line y equals x, my function y equals log base 2 of x would look something like this. My exponential function goes through x equals 0, y equals 1. My logarithm goes through x equals 1, y equals 0. So it kind of has a feel of something a little bit like a square root function. It keeps growing forever, but it's kind of concave down. It's curving down, but still growing forever. But it kind of like doesn't stop as we go to the left. It has this vertical asymptote where the closer that the input gets to 0 from above, the more negative the output. That's what happens with this horizontal asymptote on, say, y equals 2 to the x when we flip it over the line y equals x. So again, kind of crash course. You can play around with, different bases and things and see how they look on your calculator or just by writing them up by hand. But we have a bunch of properties of the logarithm. If I take log base a of a to the x, again, these are inverse functions of one another. So x equals log base a of y, but what is y? A to the x. Log base a of a to the x, the log base a and the a to the power kind of cancel each other out. They like undo each other and leave us with just the argument of the exponential, just x. Or if I have a to the power log base a of something, that's just that thing. So y equals a to the power log base a of y. These two properties, well, I covered up that last property a little bit, but these two properties are probably, practically speaking, the most important properties. And that is that logs bring powers down. So log base a of x to the n, that power n becomes a factor in front of the log. It's n times log base a of x. So when I have really strange exponential type functions, if I need the power not to be in the power, if I hit it with a log, that's going to help a lot probably. Also, the log of the product is the sum of the logs. So logs turn products into sums. So they kind of distribute over products, but when they do that distributing, they turn the product into a sum. Combining these two with, say, a -1 power, like x times y to the -1 would be x over y. And the log of the quotient is the difference of the logs. And we also have a change of base formula. What if I wanted to say, well, log base a of x, what is that in terms of a different base for a different log? Well, it turns out that log base a of x equals log base b of x over log base b of a. But a and b are just numbers. They're just bases. They're not variables. Log base b of a is just some number. So I just have log base a of x is just some number times log base b of x. In other words, essentially, like all logs are kind of the same as one another. They're just off by a scaling factor. And in fact, in a lot of applications, particularly like computer science, they just say like, oh, this, whatever, that this type of algorithm is like, order n log n. It doesn't even matter what the base is, because just knowing that it grows, say logarithmically or like n log n or something like that, that's the important part. Whether you're using this base or that base, it's just a scaling factor. And in some cases, that scaling factor is really important. If I told you that you were going to make this amount of money per year or 5 times that amount of money per year, that's a big difference. But if you're looking at, like if I increase my problem to a problem that's 10 times or 100 times or 1,000 times its size, if I want to scale this up from a little toy problem I'm doing to actually running, a server or something like that, or running a business where I'm going to have thousands of people interacting with this. How is that going to scale? Well, then the constant means a little bit less, right? 5 times as much computing power is not a big deal whenever, scaling it up to production might cost you 10,000 times the computing power. So you're much more worried about the uh, kind of the functional part. Does it grow logarithmically or linearly or quadratically, or a lot of things grow like n log n. So a little faster than linearly, but slower than quadratically, in other words. Like good sorting algorithms grow like n log n in the size of the stuff that you want to sort. Okay. We also, oh no, yeah, I mentioned the change of base. Yeah, we also have notation. So some common logarithms that, well, one of these is actually literally called the common logarithm, but some logarithms that pop up often enough that they get their own notation. Well, there's the log base e of x. So that natural base e that, the mathematicians love because the derivative of e to the x is e to the x. It gets a special name, ln of x, and this stands for the natural logarithm, ln. This is the one that we'll use the most often in this course. It just has some nice properties, some nice mathematical properties. Engineers love log base 10 of x. So it just works really nicely with the metric system and, base 10 numbers and all of that kind of thing. So log base 10 of x just gets the name log of x. I guess the engineers beat the mathematicians to it, and they got to call their logarithm log of x. So if you see log of x with no explicit base written, it probably means log base 10 of x. Log base e is usually ln of x, natural logarithm of x. And the computer scientists, they like log base 2 for obvious reasons, bits and binary and all of that. And that's often abbreviated log of x. However, if the context is clear, like you'll see in computer science, they just write like, n log n, and this is meant to be like base 2. So if the context is fairly clear, or if they don't really care about the scaling factor as much as the actual, whether it's log or linear or quadratic, you know, uh, so some people use the notation a little bit more freely than here, but I will try to stick to this notation. And for the most part, we will use natural log in this course. But your calculator can definitely do log and lg and all of these. Log is one of the standard buttons on like the TI-83, and lg I think you can find in the functions menu somewhere or something. Okay, any questions on any of this? All right, let's go through this last theorem, or this one theorem, just to kind of wrap up this conversation on logs. And then when we come back, we'll take a look at logarithmic differentiation, things like, this, for instance, or some other examples down here. So derivative of a to the x, we're saying is a to the x times natural log of a. Remember, derivative of e to the x is just e to the x. Does that mesh with this theorem? Well, derivative of e to the x should be e to the x natural log of e, but this is log base e of e. But remember, if we have log base a of a to the x, that's just x, or log base e of e to the 1 is just 1. Log base e of e to the 1 power is just 1. We're multiplying, so of course that is just e to the x. So this does mesh with our prior knowledge. That's a good thing to check with any theorem. So what is the proof of this? Well, what is a to the x? Um, where did I? Here. This is a to the power, or okay. What is a? This is e to the natural log of a. Yeah. So that's what I want to do. Confuse myself here because I have a being used one way up here and a different way down here. But if I have base to the log base of something, that's something. If I have base to the log base of something, that's something. My a is just playing different roles in the two different places. Sorry about that. But a equals e to the log base e of a. The e to the power and the log base e kind of undo each other. They're inverse functions. So this means that a to the x is e to the log base a to the power x, or that is e to the power log of a times x. But now I have a to the x written as e to the stuff. And I know the derivative of e to the x is e to the x. So the derivative of a to the x is the derivative of e to the log of a times x. But by the chain rule, this is just e to the stuff, right? The derivative of e to the stuff is e to the stuff times the derivative of the stuff in the exponent. The derivative of constant times x is just constant. And e to the log a times x is just a to the x. So that's a to the x times log a. And that's our proof here. So we now can differentiate any exponential function, again, provided it meets the criteria for an exponential function. Any questions on anything from today?